Welcome to this discussion on quantum numbers that are allowed by quantum theory. They fall in a pattern, and we will observe the pattern. Each combination of quantum numbers is given a label, and we will determine these. We will also determine how many electrons have a given label. Let's use a 6-column table that will allow us to keep track of the pattern of allowed quantum numbers, the labels used, and the number of orbitals and electrons with those labels. As with the Bohr model of the atom, the lowest value of n is n equal 1. There is only one allowed value of L, which is 0. When L equals 0, the only allowed value of m sub L is 0. The label we give to the orbital with this combination of quantum numbers is 1s. There is one orbital with the 1s label. Recalling that the m sub s quantum number can take on two values, plus 1/2 or minus 1/2, there are two electrons in the 1s orbital. The second value of n is n equal 2. When n equal 2, there are two possible values of L, 0 and 1. When L equals 0, m sub L equals 0. But when L equals 1, there are three possible values of m sub L, minus 1, 0, and plus 1. The label we put on the orbital with L equals 0 is 2s. The label we use for the orbitals with L equal 1 is 2p. While there is one orbital with the label 2s, there are three orbitals with the label 2p, which result from the three combinations of quantum numbers: 2, 1, minus 1, 2, 1, 0, and 2, 1, plus 1. The 2s orbital holds 2 electrons. The 2p orbitals together can hold 6 electrons. Altogether, the 2s and 2p orbitals can hold 8 electrons. When we look at the periodic table, we find that the first period can hold 2 elements, while the second period holds 8 elements. Coincidence? Maybe. Let's move on to the case where n equals 3. There are three possible values of L, 0, 1, and 2. Notice this column always starts with 0. The allowed values of m sub L are as before, with the addition of the values of, you guessed it, minus 2, minus 1, 0, plus 1, and plus 2 when L equal 2. The labels we place on the orbitals are 3s, 3p, and we introduce 3d. There is one orbital with the label 3s, 3 orbitals with the label 3p, and 5 values of m sub L, or 5 orbitals, with the label 3d. Multiplying each by 2 gives 2, 6, and 10 electrons. Note that the L equals 0 quantum number corresponds to the label s. When L equals 1, we find orbitals with a p label. Also notice the triangular pattern formed in the m sub L column. Finally, for all of the n equal 3 orbitals, there are a total of 18 electrons. Returning to the periodic table, we find that the fourth period is 18 elements across. It's beginning to look like there is a relationship between quantum numbers and the structure of the periodic table. With the pattern for n equal 3 in hand, you try to fill in the table for n equal 4. Pause the video and give it a try. How did you do? There should be 4 values of L, again starting with L equals 0. The m sub L column should again take on the familiar triangular pattern, with the values for L equal 3 stretching from -3 to +3. The labels now carry the number 4 with S, P, D, and now F. The number of orbitals, which you may have noticed comes from the number of values in the m sub L column, also forms a pattern, 1, 3, 5, and 7. Since each individual orbital can hold 2 electrons, we have 2, 6, 10, and 14 electrons. The total number of electrons with n equal 4 is 32. Returning one more time to the periodic table, we see that the 6th period has 32 elements. Again, the layout of the periodic table seems to be related to quantum numbers. We finish with a bit of terminology. All of the orbitals with n equal 4 comprise the n equal 4 level. There are 16 orbitals that can hold 32 electrons in this level. In the n equal 4 level, there are 4 sublevels corresponding to the L values. Each sublevel has a different label, 4s, 4p, 4d, or 4f. These are also sometimes called shells and subshells. The terms levels and shells can be used interchangeably. Hopefully, now you can see the pattern established in the quantum numbers. This should tell you what values are allowed and to predict the values in higher n levels. We also now see that the ideas of quantum theory can be considered the source of periodicity in the elements.